A car of mass 1,200 kilograms tows a caravan of mass 900 kilograms, first along a horizontal road with acceleration f, and then up an incline alpha to the horizontal road at uniform speed. The force exerted by the engine is 2,700 newtons. So let's look at the force on this system. We could treat the system as consisting of caravan and car. The force exerted by the engine is a force to the right. It has a magnitude of 2,700 newtons. We have friction and air resistance, which amount to 150 newtons on the car and 240 newtons on the caravan. We can actually take the entire system. So the resistive forces on the system are the sum of these two forces here, 150 plus 240. So the force of the engine acts to accelerate the system to the right. The resistive forces act in a direction opposite to the direction of motion of the system. Resistive forces always act opposite to the direction of motion. So that's the 150 plus 240 giving 390. So in the first question we have to get the acceleration f of the car along the horizontal road. So first of all, let's get F resultant. That's the resultant force on the system. Well, we take directions to the right as being positive here, just for this section now, just for the section on the horizontal road. So we see that this vector here is going to be positive, 2,700 newtons, but this vector will be negative. So we just add the vectors. Basically, we take this vector and add it to this vector. So the signs give the directions for linear motion. So we get resultant force 2,310 newtons. Now, how do we get the acceleration of the system? Now, this is where we use Newton's second law. Newton's second law of motion says that the resultant force on an object, I'll write Fr, meaning F resultant, is or the system is the mass of the system multiplied by the acceleration of the system. The acceleration of the system happens to be called F here. It doesn't matter. We can call it A, whatever. We get A equals the resultant force on the system divided by the mass of the system. So the resultant force is 2,310. The mass of the system is the mass of caravan plus mass of car. So it's 900 plus 1200. That's 2100. So we get an answer of 1.1 meter per second squared for the acceleration of the car along the horizontal road. Of course, the acceleration of the car is the same as the acceleration of the caravan. It's the same as the acceleration of the system actually, because the car and caravan are connected. In the second question, we want to get the value of alpha to the nearest degree. So now we need to consider the system, which consists of car and caravan, moving up this incline. So I'll just draw a box around this to show that we're talking about a system, all one system. We need to get the forces acting on it. Well, we still have the force due to the engine, which I'm assuming has not changed. I'm assuming that the force due to the engine is still 2,700 newtons. And the resistive forces, which consist of air resistance and friction, are 390 newtons. What the other force is the resistance force, 390. So that was just the sum of 150 plus 240, same as before. I'm assuming the resistive forces are the same due to friction and air resistance. Now the acceleration of this system is zero when the system is moving up the hill. How do we know that? Well, we're given that the system moves up an incline with uniform speed. Uniform means constant speed, which means the acceleration is zero. If the acceleration is zero, it means that the resultant force, which by Newton's second law is mass times acceleration, is going to be mass times zero, which is zero. The resultant force will be zero. So we have these two forces acting on the system, same as before. But we have to consider the weight of the system now. Before, we did not have to consider the weight. Well, you might say, oh, but there was a force acting down. We didn't consider that. Yes, that's true. There was a force acting down the weight of the system, but there was an equal and opposite force acting upwards. So these two cancel out. So the sum of these two vectors was 0. So we only had to sum this vector here and this vector here to get the resultant force. That's not the situation now, because the weight force is acting in such a way that it has a component in this direction. Okay, there is a normal reaction like this, but this weight force has a component in this direction that we need to take into consideration. So we're interested in forces along the incline. The resultant force along the incline must be 0, because this system is moving up the incline with a constant speed. Call it v, or whatever we want to call it. V is constant. So if the system is moving at constant speed up the incline, it means the resultant force along the incline is 0. So we're only interested in forces along the incline. We won't be interested in this force here, because that's not along the incline. Actually, this force here will be counterbalanced by this force here, because the system is not moving perpendicular to the incline. It's not moving away from the incline, or it's not moving down through the incline, obviously. It's just moving along the incline. So these forces will cancel out, so we can forget about them. They're not going to come into this. So what we're interested in is this here. This is the component along the incline of the weight of the system. What's the weight of the system? Well, it's the mass of the system times g. That's the weight of something. What's the mass of the system? It's 900 plus 1200. What's that? That's 2100. 2100 kilograms, and we multiply that by g, so we get 2100 g newtons. And we want this component here along the incline. So we have this right angle triangle here. What's this angle up here? Well, better question might be to ask, what is this angle here? This angle is actually alpha. This angle is actually the same as this angle here. One way to see that is to realize that this angle up here is 90 minus alpha. If we complete a triangle here, a right angle triangle, in this right angle triangle, this is alpha, this is 90, so this angle in here is 90 minus alpha, or this angle here. If this is 90 minus alpha, this must be alpha, because these two angles have to add up to 90 degrees, because the third angle is 90 degrees. Another way we could look at this is to say that we have these two lines here are perpendicular to this line and this line. So if we have a pair of lines that are perpendicular to another pair of lines, then the angles between these pair of lines must equal the angle between this pair of lines. That's another way you could remember this. So anyway, we want this vector here. So this vector is the side opposite this angle alpha in this right angle triangle. Here's the right angle. So it's opposite alpha, so that's sine. So we need to take the hypotenuse of this right angle triangle, which is 2100 g, and multiply it by sine alpha. Because this side here is opposite alpha. The sine of alpha is this side divided by the hypotenuse. So it would be 2100 g sine alpha divided by 2100 g, which would just give us sine alpha. So now we can get the resultant force on the system along the incline. So we could take this direction as being positive. So this vector here is 2700 newtons, it's plus 2700. And then we subtract off these two vectors, 390, because this is a negative vector, it's pointing opposite to the positive direction, which is up the hill, minus this vector here, which is a negative vector. And that must equal 0, because the resultant force along the incline is 0, as I've said already. So from this we can actually solve to find out what sine alpha is. So simply rearranging here, we get alpha is 6.44 degrees. So alpha has to be 6.44 degrees for the resultant force on this system to be 0. Well, the resultant force along the incline will be 0. But the resultant force perpendicular to the incline is 0 as well, because these two cancel out because the system is not accelerating perpendicularly to the incline. So the overall resultant force on the system is actually 0, you could say. If alpha was some other value, then we don't get 0.